With raindrop-driven erosion, transport mechanisms vary with flow conditions. And because flow conditions vary along an eroding surface, the spatial distribution of the detachment and transport mechanisms vary along an eroding surface. Generally, these different situations depicted here depend on rainfall intensity, slope gradient and slope length, and time, and the temporal and spatial variation in transport mechanisms control how soil loss varies during an experiment. In many experiments, splash erosion occurs at the beginning of an event to generate detached material that is subsequently transported by rain-impacted flows by raindrop-induced siltation and rolling. Particles transported by raindrop-induced siltation and rolling travel at various rates over the surface and take time to move down over the slope. As a result, the particle size distribution of the sediment discharge varies with time during an event. In this example, the rate that particles move across the surface varies from left to right. The steady state occurs when enrichment is 1 for all particle sizes, and that occurs after the slowest moving particles detached at the start of the event is discharged. Here are two examples where not all the particles detached at the top of the slope reach the bottom of the slope before the experiment is finished. There are cases where flow-driven siltation and rolling control the movement of particles passing over the downstream boundary. In this case, we have a raindrop-induced siltation zone, below which there is a raindrop-induced siltation, then flow-driven siltation zone. Any drop impact in that bottom zone will cause sediment discharge. However, material entering that zone from upslope where flow-driven siltation occurs will be discharged without further involvement of raindrop impact. In effect, this increases the value of X for that drop that caused that raindrop-induced siltation to occur. Other particles of different size and densities will still travel over the boundary by raindrop-induced siltation. So we have situations C and D occurring at the same time. This is a model of raindrop-induced siltation, where the distance particles travel varies with particle size, density, flow depth and velocity. And in this graph we have flow velocity at the bottom of a 2-meter long slope and the critical velocities for flow-driven siltation of 0.46 mm coal and 0.1 mm sand. When slope gradient exceeds 30%, flow-driven siltation moves coal particles across the downstream boundary. As the area of flow-driven siltation increases, so too does the discharge of that coal material. However, particles of sand still are transported across the downstream boundary by raindrop-induced siltation.